And today we will be discussing impulse. That is the topic of today's notes. So we are going to explain how an impulse causes a change in momentum and to apply the impulse momentum theorem to solve for variables such as impulse force, time, change in momentum, and change in velocity for various scenarios. Again, this is the first set of notes for Playlist 4, which officially begins today. You do have some other due dates upcoming, including another roller coaster Q&A day where you can plan and revise preliminary data if necessary on the 6th. And you do have a bump assignment that is due in a little less than a month. So you should be looking at that if that's something that you're planning to do. All right, so before we talk about impulse, we need to quickly remind ourselves or remember back to momentum. I'm on slide 83. So again, momentum refers to the quantity of motion that an object possesses, or mass in motion was the kind of shortened definition. And thus far, our discussions regarding momentum have focused only on constant momentum for objects moving at constant velocity. So you had scenarios where you had a ball rolling at a constant speed of 3 meters per second, and that ball had a mass of 2 kilograms, and you had to find its momentum. Okay, but today we are going to talk about how to change linear momentum of that constant velocity system, whatever it may be. Okay, and if we want to do this, we have to change that velocity, and we can do so by causing acceleration. Okay, so if we have acceleration of our system, we will then have a change in velocity and thus a change in momentum. How can we change velocity? How do we make something accelerate? Push it, sure, that's one answer. Apply some kind of net external force to the system. Okay, if you have a net external force acting on your system, then you will have a change in your velocity. You will have acceleration of the system, a change in the velocity of the system, and thus a change in momentum. This will cause acceleration according to Newton's second law, and this is the equation that we learned way back last semester, but that the acceleration of your system is equal to the net force applied divided by the mass. Or you oftentimes see this written instead as F net equals MA. Okay, but again, we can look at what that acceleration will be and kind of work from there to figure out what our new velocity will be and our new momentum will be, but we're going to get a more streamlined way of solving that type of problem. Okay, so let's go ahead and derive an equation that we can use for change in momentum. So I'm going to start with our Newton's second law equation that says that the acceleration of the system equals the net force divided by the mass. And I know from previous notes from the beginning of the year that acceleration is the rate of change in velocity. It's your change in velocity divided by time. So I'm going to go ahead and substitute that in there. And then from here, if I want to get an equation for change in momentum, I'm going to go ahead and cross multiply, okay, so that I get this equation. M times delta V equals F net times T. But this is actually the impulse momentum theorem on my screen right now. Okay, we'll get to what that means in a minute. But we're not finished for what I want to do. So I still want to derive an equation for change in momentum. So I'm going to go ahead and expand that delta V. I know that that is change in velocity, and thus it is final velocity minus initial velocity. And so I have M times V minus V naught equals F times T. And I'm going to go ahead and distribute that mass into those parentheses to get this. MV minus MV naught equals F net times T. And I know from my definition of momentum that mass times velocity is momentum, which means I right now on my screen have momentum, or final momentum, minus initial momentum equals F net times T. And I know that final momentum minus initial momentum is change in momentum. You could stop at any one of those steps, and there's several different equations that you have up there that you could refer back to depending on what you're trying to solve, or you could go through this derivation again on your own. But when we look at change in momentum, yes, it could be mass times change in velocity. We just talked about the fact that that's one way to change momentum, is by changing velocity, but there is another equation that allows us to solve for change in momentum, and that is net force times time. Okay, so depending on the information you have, one of those might be more useful than the other. Okay, so changing the velocity of an object will cause a change in momentum. This is also called an impulse. Okay, so look at those units. Change in momentum is impulse. Change in momentum is mass times change in velocity. Impulse is net force times time, and we just showed that those were equal to each other. If you look at the units, your mass units are going to be in kilograms, your velocity units will be in meters per second, thus the unit for change in momentum is a kilogram meter per second, whereas force and time are in newtons and seconds, and so that is a newton second, but those are the same unit. Okay, a kilogram meter per second is a newton second, and that is because a newton is a kilogram meter per second squared, and a kilogram meter per second squared times a second is a kilogram meter per second. Okay, so those are two different units that you could use if you were solving for change in momentum or for impulse. Mathematically, they are the same thing. Okay, so what is an impulse? I've used the word a couple times now. It is a vector quantity that results from a net external force applied over time, causing a change in the system's linear momentum. The equation I just showed you a second ago gave that away. It was force times time. Okay, so if you apply that force for a certain amount of time, you will have a change in the velocity of your system because you have a net external force being applied, and thus a change in momentum of your system. Sorry, I switched that too fast. Let me give you all a moment to finish writing it first. Okay, but again, it is a vector, so that does imply that impulse does have direction, so both magnitude and direction. And again, the formula for impulse is force times time, or you can set it equal to change in momentum, which means you can also set it equal to mass times change in velocity. We had all those equations up there on the board a minute ago, all set equal to each other at different stages in our derivation. All right, so again, it is a vector, so direction matters. Sorry? Okay, what can you say about the final momentum when your net force is applied in the same direction as the system's initial momentum? In other words, let's say my system is a ball rolling across the floor. Okay, if the ball is rolling to the right, and I also apply a force to the right. Okay, if my force is in the same direction as my system's momentum, I should have a scenario where my final momentum has increased from my initial momentum value. It got faster, okay, because I pushed it in the same direction it was already going. And so I would have an increase in the initial momentum of the system, giving me a larger amount of momentum at the end while maintaining the same direction. So it's still going to the right in that particular example. Okay, so if your net force is applied in the same direction as your initial momentum, in the same direction as your velocity, okay, then you are going to end up with a greater amount of momentum than you started with. You can write that in whatever words you need to. And again, guys, if you can follow along on your own screen in case I go too fast, this is slide 88. Okay, but again, velocity will get faster. All right, what if your net force is applied opposite the direction of the system's initial momentum? So same type of scenario. Let's say the ball is rolling to the right across the floor, but I start pushing to the left against the ball. Okay, well, it depends on how much force I use. It's possible that I use just enough force to slow it down, maybe even stop it. Okay, that's possible. Okay, that I apply just enough force to cause it to slow down, maybe to a stop. Okay, in that case, I would have that smaller net force that I apply would result in a decreased linear momentum, again, possibly to zero. So I would be slowing it down, maybe even stopping it, depending on exactly how much force I apply. But there is another scenario that is possible. What if I apply more force than is needed to stop it? What do you think would happen? Yeah, I would change direction. Okay, so it is possible if you apply more force than is required to stop it, that larger net force would result in decreasing momentum all the way to zero, and then it would start increasing in the opposite direction, increasing magnitude of linear momentum by changing the system's direction of motion. If my ball, let's say, hit the wall, it would likely bounce off unless it was rolling, slow enough to just stop. Okay, and so that force, if it's sufficient, can cause the change in direction of your system's motion. All right, when we discuss impulse and these forces that change the momentum of the system, do we discuss constant forces? Not necessarily. Okay, the forces that we discuss could be constant, or they could be changing amounts of forces. If you look at a collision, typically there is a changing amount of force. I'm going to show you a graph of what that looks like later on in the notes, but it's not necessarily always a constant force. It could be an amount that increases and then decreases again. Okay, but if your net force is a constant value, then you can use the equation that your change in momentum would be equal to your net force times your time. However, if your net force is continuously changing in magnitude, you really would need calculus to solve this and get an actual value. However, we are going to approximate it using the equation, our change in momentum delta P equals our average force. If it's changing, we're going to use the average times time. All right, so let's look at this graphically. Okay, so in this graph, how can I find change in momentum? This is a force time graph, and you can see that I have a couple times labeled T1 and T2. I have initially no force and then a bunch of force, whatever this value is, applied between T1 and T2 and then back to no force again. Okay, so is this constant? Yes. Okay, this is a constant amount of force applied between T1 and T2. It's a horizontal line. And so I could use this equation and say that my change in momentum, or my impulse, but delta P equals my net force times my time. And if I were multiplying net force times time, I would be finding the area under the curve, or really this rectangle on my graph. And so it'd be the area of this region right here, where I would just take and multiply that force by the amount of time, which is the equation, force times time, ends up being length times width of that rectangular shape of my graph. Okay, so again, if you have a constant force, that's the equation you use. But this is not super realistic. Okay, it's very difficult to have a sudden force that you didn't kind of build up to, if you will, even if that buildup was really quick. Okay, and so real world, our graphs tend to look like this instead. Okay, and you need to do the same thing. You need to find the area under that curve, which means, again, that you truly need calculus. You need to find the integral. Okay, however, we're not doing that. We're going to approximate it by using the average force. So I would take my max force, okay, and my average force, I'm going to say, is half that. Again, this is going to be a rough approximation. So I'm going to say this is half my max force. I'm going to call that my average force. And I would take that half of my max force and I would multiply it by the time. Okay, and again, it'll give you an idea that it'll be at least somewhat close to what you would actually get with the calculus. Okay, but that's the equation if you don't have a constant force, is you would take your average force times your time, and you're going to use half that max value as your average. Okay, note that these times are really short. If this is a collision, like a ball hitting a wall, the collision doesn't take 3 seconds. It happens almost in an instant. If you look at my x-axis, my times, they all say times 10 to the negative third. I'm working in milliseconds here for these numbers. It's not 4 seconds, it's 4 milliseconds. And that would be what you would expect to see on a graph for a collision. It should be pretty slow. Or not slow, quick, rather. All right, so let's try an example calculation problem. This one says a ball of 0.05 kilograms moving at 53 meters per second collides with a bat, resulting in the ball moving at 45 meters per second in the opposite direction. If the collision occurs in 6 milliseconds, what is the average net force that the bat applies to the ball? Again, we need to define our system before we can do anything else. We've been doing this entire unit. Our first step should be determining what our system is. Because we're trying to find average net force, we need to define our system so that we have a change in momentum, so that we can use our change in momentum equation that we just learned that has net force in it. And so we need to define our system so that it is open, meaning I just want it to be the ball so that the bat applies a net external force to it, causing the ball's motion to change. Okay, so the system here is going to be the ball. I'm going to go ahead and now label the information that I have been given. So the given information, I know the mass of the ball is 0.05 kilograms. I know that it has an initial velocity of 53 meters per second, that it has a final velocity of 45 meters per second, and that the time of the collision is 6 milliseconds. Okay, I'm looking for the net force, and so I've labeled some things up here, but I do have one thing that I want to mention that I need to address here. Did you already catch what it is? Yeah, my velocities, right? When you read the question, it says the ball is moving 53 meters per second and then it's moving 45 in the opposite direction. I do need to identify what the positive direction is because these should not be in the same direction. One of them needs to be negative. I'm going to go ahead and call my final velocity negative 45 meters per second, meaning that the initial direction it was moving was positive and now it's moving in the negative direction. But you do need to have one of them be negative. It doesn't necessarily matter which one. You're going to get a different sign potentially on your answer depending on how you define that, but you need to define it if it's not defined for you. All right, the other thing I need to do for my calculations is I cannot use milliseconds in the calculation. I need to get that into seconds instead. There are 1,000 milliseconds in a second, so 6 milliseconds is 6 times 10 to the negative third seconds. You can also put that just as a decimal if you don't want to use scientific notation, but you do need to convert it. Okay, so from here, we're going to go ahead and put down our equation that we derived a minute ago. We're trying to find average net force, so this is a better equation for me to use than mass times change in velocity because I'm not looking for mass nor am I looking for change in velocity. So I'm instead going to use this equation. My change in momentum is equal to my net force times my time. Again, I need to arrange this equation so that it is set up to solve for net force and so that it has all variables that I know. Okay, I don't know delta P, so I don't want to leave that in there. And again, I need to rearrange it also. But I'm going to change that to, instead of delta P, P minus P naught. That's my change in momentum is my final momentum minus my initial momentum. And I know as well that momentum is mass times velocity. So my final momentum would be mass times final velocity. My initial momentum would be mass times initial velocity. So now I have mv minus mv naught equals net force times time. Okay, and now it looks like I have the variables that I need. Okay, if you look at the list of variables that I've labeled as my givens, I have everything that it needs to go in there. The only thing I need to do is rearrange this so that it is set equal to net force, and I can do that by dividing both sides by time. And so now I have that my net force is equal to mv minus mv naught, all of that over t. And this is where I can substitute in my numbers. So if I plug in the values that I have in this question, my mass is 0.05, my final velocity is negative 45, my initial velocity is 53. Of course, the mass doesn't change. So I have that as my numerator, and then divided by my time, 6 times 10 to the negative third equals net force. Okay. Again, from here, you just put this into your calculator, and you should get a net force of negative 816.67 newtons. Does anyone have a question about this particular example? I'll give you a moment because I know some of you are still writing. Okay, but this is how you're going to do a change in momentum or an impulse calculation. We've got a few different equations that you can use. All right, guys, so that is going to bring us to the end of today's notes. For the rest of the class period today, you can work on playlist 4, which includes the workbook practice, that should say, is on paper. There is a copy of it up here at the front of the room if you haven't grabbed it yet. You do have my Up and Math assignment and the quiz. The checkpoint is in AP Classroom. There is a new assignment that I have listed down here on one of these bullet points that is in Schoology, and it's called Center of Mass and Systems Review Homework. I'm going to post it in Schoology, and I need to add the link to My Open Math as well. But that I just need you to get done by Friday. Okay, there's a couple things that we need to kind of go back over a little bit more in depth that we didn't quite cover as much as I wanted to. And so I threw that together. It's got 10 questions and they're answered in video clips. So you just have to watch 3 video clips that are, 5 minutes long or something, and answer some questions that should hopefully clarify if you're having questions still about systems or center of mass. Hopefully that provides some clarification for you. But I would, again, like you to have that done by Friday of this week. And then your bump assignment is due by the 23rd of February. And again, you do have a roller coaster deadline coming up as well. All right, guys, go ahead and get to it. If you have questions for me as you're working, please let me know.